Right now, we present preliminary Internetworking simulation of the QB50 Cubesat Constellation by Héctor, Bedón, Carlos, Negrón, Jorge, Llantoy from National University of Engineering, and Carlos Miguel from Technical University of Madrid and Cem Asma from Carmen Institute.
Well, good evening, foreign and Colombian authorities, students and teachers. Thank you for inviting me. I'm here. My name is Montoya, and my paper is entitled Preliminary Internet-Working Simulation of the QB50 Cubesat Constellation, of which the paper ID is 72749. My team is formed by Master of Science Héctor Monzón, who is currently an only full-time professor. Myself, Montoya, Jorge and Parra. Jorge and me are 2010 graduates, and with support from Carlos Miguel Nieto from the Universidad Politécnica de Madrid, and Dr. Cem Ozan Asma from the Monzón Institute of Belgium. Me, Mr. Héctor Bedón, and Jorge Llantoy are from the Universidad Nacional de Ingeniería de Perú, the National University of Engineering. Well, let's take a look to the overview of the presentation. Why the paper? Well, there is a possibility of my university of participating in the QB50 project through the Centro de Tecnologías de Información y Comunicaciones CETIC-UNI, the Information and Communication Technology Center, using a homemade, developing a double CubeSat, which is a small satellite of 20 per 10 per 10 cubic centimeters. Well, the QB50 project was proposed by the Monzón Institute of Belgium. It is formed by 50 CubeSats carrying identical sensors to be launched to the upper atmosphere. It requires specific protocols in order to achieve the planned objectives, depending on the service. The project goal is to study locally the temporal and spatial variations of several parameters, in more specifically the lower thermosphere, which is between 90 and 330 kilometers of altitude. It's such a very hard goal to achieve with normal satellites, because it's very expensive to use a very huge amount of satellites. But nevertheless, little CubeSats considerably reduce the cost. So, well, the objective of this paper is to evaluate the performance of transmission control protocol and user datagram protocol, which are well-known transport protocols, over a hypothetical QB50 network. Because this QB50 network is currently being developed and has a lot of stages, so there are a lot of years. It's planned to launch on 2013. So there are two different scenarios that are considered as a result from the preliminary QB50 research that were carried out. So, well, let's take a look at the two topologies for scenarios. The first scenario is a ring of 50 equally spaced CubeSats. Look, there's an equal space between each satellite. And the second one, 10,000 kilometers long CubeSat string. I say a string because it's just a 90 degrees string of CubeSats, and the separation among them is a quarter separation than the first one. Well, an interesting note, these graphs were obtained with the study software for Linux. Okay, and there's the web page. Well, let's take a look to the parameters about the simulation. In this investigation, inter-satellite links are proposed for the project, although this isn't yet a mandatory fact for the actual project. Well, this simulation is made with the NS2 software, very well known, installed on Linux, a virtual machine. Well, the simulation needed a TCP Westwood New Reno package for NS2 created and edited by the California Institute of Technology, which published the algorithm in order to allow the free use of it. Okay? Well, it's one sole polar plane. The height of the satellites is 200 kilometers and the inclination is 79 degrees. There are a lot of ground stations models in the scripts, in the algorithms, But the only one that matters is one in Lima, Peru, which is constantly receiving the data. The uplink and downlink bit rates is of now 9,600 bits per second. The intersatellite links curves that are shown in graphs are of half a kilobits per second, 1, 3, 6, 8, and 10. Transport protocols, as I have already mentioned, UDP and TCP westward with mirroring features. There is a link layer, obviously, but it's connectionless, best effort. The error model is 1/10 per second, and neither FEC nor ARQ models in this link layer. Three parameters are measured in this paper. First, the throughput to limit. This is the quantity, the rate of bits received by the ground station. Then, the delay from the satellite number 0 to limit. And then, 3, the packet loss rate. Well, the throughput is measured every 40 seconds for UDP in both scenarios. And for TCP, it's 200 for the first scenario and 140 for the second scenario. The total simulation time is 1,500 seconds for the first scenario and 700 seconds for the second one. Why 700? Because after 700, because it is just a string, all the satellites begin to lose line of sight. So there's no communication. Okay, and the NS2 trace shows continuous handovers among satellites, where packets travel through the intersatellite links until they find a satellite that is available to download the closer satellite to Earth, and it downloads the data. Let's take a look at the traffic flows. As you can see, there are 5 flows. Packets shall travel across the intersatellite links until they find a satellite, only one, as close to him as possible, using a simple routing algorithm. The packets of 210 bytes are sent every second. It's a constant bit rate. We can consider it like, for example, video streaming for the satellites. It can be every 1 second or half a second. The idea that I want to explain is that it's constant bit rate. And well, NS-subplot add-on software was used for making this map. Well, the initial types of traffic shown satellite are sent gradually for both topologies. Packet loss results and some other details are shown in order to summarize, but relevant aspects are properly commented. So it's gradually. First the satellite 0, then the satellite 9, and 19, and so on. Well, let's rush. Let's now go to the first result. This is the result for the throughput that performs in such a staggered manner. Each step is of 1,068 kilobits per second. That is the average rate of the constant bit rate sources. Packets are sent as soon as are produced by the constant bit rate NS2 agent. The delay, well, the high ISL bandwidth values shows low delay, but the channel errors and congestion causes packet loss as the intersatellite link bit rate is low. Well, and here it can be shown that satellite 0 begins, satellite 9, and then so it causes a variation. What happens with TCP? The TCP, well, has a congestion window mechanism. The overhead, well, there is an overhead where bytes are grouped, then reassembled, and then sent. How are they sent? Well, acknowledgements return rate is measured, so the bandwidth is a function of this return rate of the acknowledgements. Let's see the delay, the delay of the first scenario for TCP. The high delay, there is a high delay because of the congestion window and the overhead. Bytes are grouped and reassembled again, but the packet loss is too low. I don't show every graph that is obviously in the proceeding because this is just an overview and I don't have enough time. Second scenario, well, for the second scenario for UDP, since approximately 540 seconds, this is shaded. Performance began to drop because the satellites began to lose the line of sight. So there is a saturation in the extreme intersatellite links. So this is shaded and it's I call it loss, because line of sight loss. Well, the delay is similar to first scenario, but the aforementioned saturation causes even higher packet loss and delay. Well, for TCP, the saturation doesn't cause delay or packet loss. There's no problem. But anyway, the throughput is reduced because the congestion window senses that there is a saturation and lowers the throughput. Well, again, for the delay, it's reduced, but it's higher for TCP again. The packet loss is too low. So what are our conclusions? Well, the impact of the intersatellite links bitrate was explored within both topologies. The TCP performs better than UDP for throughput and packet loss, but the UDP delay is lower, as was predicted, and this obviously happens in terrestrial networks. The transmission control protocol is ideal for reliability, for example, FTP applications. But UDP is ideal for quick data delivery in satellite services. For example, real time. Again, the same as terrestrial networks. There is a relation between downlink bandwidth, the intersatellite link bandwidth, and the traffic to be generated. And this is very important. Well, after having the results of this paper, now we are able not only to simulate the traffic in satellites, but also to prove the protocols on wireless mobile terrestrial devices as an interesting matter of further investigation. Any questions? Yes?
Listening.
When you show us the condition of the simulation, I noticed that in the version of TCP, you say that you do not use any power error correction mechanism. It's not so strange because it's normal in satellite communication. They use some kind of power error correction because by the wireless nature of the communication, they have there is no any guarantee that the information is going to arrive. Because the difference is very long, it's expensive to lose a package. And use included some kind of power error correction, even if there is some modification, the protocol is able to reconstruct the package. Why this is not considered in this is curiosity.
Well, indeed, this is not an investigation of say, FTC or ARQ. We are just analyzing a very bad case in order to make in order to emphasize the performance of UDP or TCP. Yes, I can use it. There's no problem, but that's not a matter. That's not for the purpose of investigation.
Anyway, the versions of TCP you are using have this packet loss control and retransmission strategies and
yes.
all that. You just suppress that portion of the protocol.
Pardon?
You are using TCP Westwood and Negrón.
Yes.
And the whole idea of those protocols are to recover from packet losses. So they use ARQ in its heart, in its core.
Oh,
but
yes,
you are suppressing these functions, or how is it?
No, I am suppressing it in the second layer, in the link layer.
Oh, okay.
But not in the transport.
Okay.
Yes.
Just as a quick question, these are LEO satellites or?
Yes, that's a low Earth orbit satellite.
Wow.
Of course.
Any other question? No? Okay, thank you very much.